Hello class, this is CSE-5250, Section 1, Week 12, Video 8. Now, for the next two videos, and this is going to be the first of the two, I believe it's going to be two videos, but it's going to be a walkthrough on how to put together the sieve of Eratosthenes using MPI. Now, if you have a good idea on how you can put it together, then by all means, use whatever ideas you may have. Otherwise, this is going to be a tutorial video, part 1 of possibly 2 parts, where we build up the sieve of Eratosthenes using MPI, step by step from the ground up. So let's begin. So, remember that the sieve of Eratosthenes was based off of a doubly nested for loop. The outer loop iterates through a vector of numbers, finding numbers that are prime. The inner for loop iterates through the vector again and crosses out multiples of that prime number that are not the prime number itself. So, if we start with a vector filled with all the numbers between 1 and 100, we cross out the number 1 because that's non-prime. Mathematically speaking, we don't consider that to be a prime number. And then we enter the for loop, finding the first non-prime number that we find the first number that hasn't been crossed out yet. And that's going to be the number 2 because we already crossed out the number 1. So the outer for loop says, I found a prime number. And then it's going to execute an inner for loop that basically starts at 2, goes up by 2 so it doesn't cross out the number 2, and starting at that point instead, it's going to cross every other number, and those are going to be all the numbers that are divisible by 2, but not 2. So how do we translate that to MPI? Well, hopefully at the end we'll see how that entire process pans out. But first, we have to consider the fact that in MPI, we are in a way writing code for 2 programs. We can set it up like this. One process will be sending something to other processes, and those other processes will be receiving something. So, let's start small and consider a case with only 2 processes. One process sends something to the other. So we only need to deal with rank 0 and rank 1. Right, first we have to populate our program with everything that we need. We need mpi.h. We're gonna need vector because here I actually end up initializing a vector, but I never explained why we needed that in the section. But I'll get to that soon. But at the very least, we're gonna need mpi.h to start out. We need to write out our main function with the 2 parameters, argc, argv. We need to write out 2 variables, int com size, int rank. We need these 3 MPI functions, MPI init, MPI com rank, MPI com size. Between these 5 lines of code and the pair of lines of code that are MPI finalize and return 0, we can do basically anything we want between this section of code and this section of code. That includes writing in the if statement that I described here, but simplified so that we only have to consider 2 processes. Now, these 2 code blocks here, we would normally think of those 2 code blocks as being different scopes. So if I declare a variable within this code block here, this code block won't know that it exists. And the same is true the other way around. If I declare a variable here, if I declare a variable within this code block doesn't know that it exists. However, what happens if I write something outside those code blocks? Look at comp size and rank. These two are outside of these code blocks, but these two code blocks have access. They know what these two are. And the same is true for this one small vector that I'm initializing here to be 10 elements and all zeros. And it's not like they're being shared. It's not like shared memory. Rather, it's their own copy because these are literally separate processes. They might have the same variable names, though they might not necessarily have the same values. And in the case of this numbers vector here, they might not even have the same purpose. So, when you start off, we're just going to write everything in here, these 5 lines of code, these 2 lines of code, this if and else if, and we're going to squeeze in this vector of 10 zeros. So let's start off with having rank 0 populate its numbers vector with values and then send it to one other process. So comp size and rank are outside of these 2 code blocks here, so these 2 code blocks will know what they are. But as I said, the same is true for if we declare a vector outside these 2 code blocks. So rank 0 is going to know what this numbers vector is, rank 1 is going to know what this numbers vector is. I could have it so that rank 0 and rank 1 have their own separate numbers vector declared within these code blocks. That is one way to do it, but I did it this way because, well, I want to have a vector that's pre-made with the right size. That's basically it. It would work the same way if it would work the same way I would put a separate numbers vector in the code block for rank 0 and rank 1. But then I would have to make sure that they're the same size. So by declaring it out here, I basically 2 birds with 1 stone. To kill 2 birds with 1 stone saying, yeah. Okay, moving on. So both rank 0 and rank 1 are gonna be doing something with the numbers vector, but it's gonna be something different. So rank 0 is going to fill it with numbers. It's going to fill it with the numbers from 1 to 10, and then it's going to send it to rank 1. The code to fill that vector with numbers is pretty simple. It's just a for loop. Numbers I equals I plus 1. So the send function, we're going to use printf because I don't want to deal with race conditions associated with cout. So printf it's going to be MPI send has 6 parameters. We only need to deal with the first 4. The first one, the first function argument is going to be the address of the first element of the numbers vector. So ampersand numbers and in square brackets 0. The second argument is how big the vector is. So that's going to be numbers dot size. The third parameter is MPI underscore int because that denotes that we're sending integers. The fourth parameter is who's the receiver. That's going to be rank 1. the last two parameters are 0 and MPI-COM world. We won't be really dealing with these two, so just set them to 0 and MPI-COM world. MPI receive is similar, except there's 7 parameters. So, MPI send is going to be using its numbers vector. It's going to use its numbers vector as, how do I explain this? Rank 0 used its numbers vector the following way. It filled it with values, and then it's going to send us, it's going to use the values in there. It's going to use those values as a message to be sent to rank 1. Rank 1 is going to use its numbers vector a little bit differently. Rather, it's going to use its numbers vector as a way of, it's going to store whatever rank 0 is sending. It's gonna, okay. MPI receive is going to take in 7 parameters. The first one is the address of the first element of the vector that's going to be used to store the message that's being sent from rank 0. So ampersand, numbers, and in square brackets 0. Second argument is how many elements are in the vector. So rank 0 sent us 10 elements. We're going to receive 10 elements. Third parameter is MPI int because it's a data type of int. Fourth argument is 0 because that was the sender. And the last 3 parameters, we can set them to 0, MPI-COM world, and MPI status ignore. So, as I said, these two processes are using their numbers vectors a little bit differently. So it might be a little confusing that we have, it might be a little bit confusing to have these first 2 parameters be the same. But, as I said, we could have had it so that these 2 code blocks had their own numbers vectors. We would have had to declare what's kind of the same variable twice, but it's not really the same variable, really. I say variable when I mean vector, but anyway. If we had instead declared the vector separately within these 2 code blocks, we could have named it, we could have given it 2 different names. So if you want to think about it that way, if you instead had a numbers send vector here and a numbers receive vector here, if it was coded that way, it might make a little bit more sense. But it coded it this way because I wanted to illustrate the fact that you can have 2 processes use the same variables, or in this case a data structure, differently. We can then print the numbers that we received. This is more for our own convenience because, well, we just want to make sure that this thing worked. And here's a checkpoint. If coded right, we can build the program and run it with this command. MPI exec -n 2, because we want to run with 2 programs, and whatever our program name is, .exe. So I'm gonna pause the video and then I'm gonna get Visual Studio started up with all the code that we've just described. Alright, so we're back in Visual Studio and I have the code. Well, actually I had written the code already. There's about 5 stages that I'd like to get through. And here I set it to search max of 1 million. We don't really have to do that. We can just set that to 10. So this is one small deviation from the code in the PowerPoint presentation. Here I set the search. Here I already have a search max. I can just set the search max variable to whatever I want, and then I can use that to create a vector of whatever size I want. But we can just copy the code exactly, and instead of having a search max, we can just have the number 10. Okay, so here we have the code for rank 0. It's going to use its numbers vector. It's going to use the numbers vector. It's going to fill it with the numbers from 1 to 10, and then it's going to send that over to rank 1. Rank 1 is going to use its numbers vector. It's going to use it to store the message that rank 0 is going to send. So, MPI receive, number 0, yada yada yada, and then it's going to print out the numbers that it received. So, when we create a project, there was a multi-step process that I had to go through, which I'll summarize right now. First, you have to install MPI. There are 2 installers that you have to run. If you're using Visual Studio, then you have to do these steps. You'd have to go to right-click here, Properties. My face cam was in the way, so let's try that again. Right-click here under Solution Explorer. Click the project name here, Properties, and you'd have to go to a few different places and tell the project, hey, I need to include these other things. You would have to include the include directory, the library directory, and maybe a few other things. There was like 3 things you had to include. So yeah, the first one is the include directory. The second one was the library directory. And oh yeah, this was a fairly common problem. You have to pay attention to whether your program you're making in Visual Studio is set to x86 solution platform or x64. That determines which library you have to use. Otherwise, you get a version mismatch and it won't compile. But it's an easy fix. You can either go back here and set the library to the correct one, or you can just change the platform from x86 to x64, or vice versa. Then we had to add msmpi.lib, and that's basically it. When we compile this thing, well, we can compile it, but we can build it, but we won't be able to debug it using the debugger in Visual Studio. So we can build it. So once you have this code written out, we can build it, and Control-Shift-B to build solution. I realize my face is in the way again, so let's try again. Build solution, build succeeded. And now, move my face cam again because I have to right-click this again. Open folder in File Explorer. Here we open up the folder that contains our main.cpp file, and in my case, I have a bunch of text files that contains the exact code in various stages of progress. What we need to do is click this up button, or Alt and up arrow, because we have to go back 1 directory. So I can just click up here, and notice that we had a debug folder here. This is not where the executable lives. We had to go back 1. We had to go back 1 directory to find another debug folder. But that's the one that contains the executable. So once you find that, click the address bar in File Explorer, type in cmd, and then we can just type in our command to run this executable, which was npi exec-n. We want 2 processes, and then we need to type in the name of the executable itself. So in my case, it's npi underscore sieve underscore SPR underscore 2023.exe. Type that in. Rank 1 has received some numbers. Rank 0 had already sent some numbers, so it works. Okay. But that was just sending the code. That was just code to send a message from one process to another. What if we had multiple processes? Well, it's pretty simple to modify actually. What we would need to do is we would need to put this send function in a for loop, and then we would have to erase this part here. So instead of else if rank equals 1, it's else. So let's just do a more step-by-step process. Wait, that's the wrong one. So if you want to send this to multiple processes, for rank 0, as I said, we have to put the send function inside of a for loop where I starts at 1 and ends at com size. We start at 1 because rank 0 doesn't need to send it doesn't need to send to itself. And if it did, it would actually cause deadlock. It turns out that you can't have a process send and receive to itself. But even then, even if that wasn't the case here, we would have a situation where the number of sends and the number of receives are mismatched, and that also causes deadlock. The other change is this parameter, this function argument here that used to be 1 is now I, because now we want to send it to multiple processes from 1 to com size. And as I said, we can just turn this else if to just else. So minor changes. So I already have the code written up for this, so I'll just copy this, paste into here, and there we are. We have all the changes that we need. We have the for loop. We have the for loop that's executing the send function, and then we have this code block here that's no longer exclusive to rank 1. So we can build this, and since we already had the debug folder open and command prompt already running, we can type in CLS to clear the whole thing and use the up button to find the command that we had previously written and run it again. This is going to be another checkpoint, because in the slide, if this works, the code will run the same as before, except there are more processes that have received some numbers. That's actually the wrong slide. It's actually this one. Rank 0 sends some numbers, and ranks 1, 2, and 3 receive some numbers. So let's see what that looks like for ourselves. There we go. Rank 1 receives some numbers, rank 2 receives some numbers, rank 0 is sending some numbers, rank 3 receives some numbers. There we are. Now, it's not exactly the same as what you may be following along with, because, again, I have this search max vector. I have a search max here that I've declared. So what's happening in this code is I'm actually creating a vector with a specified search max. I had that set to 1 million, and that's why it was a little bit slower than what you might be trying out if you're trying this out step by step following along. Really, the search max shouldn't be here. It's just something that I wrote in because I wanted to get ready for the next part, which is to specify a search max. But anyway, we can just, as I said, we can just have that be a fixed value. That's part of this. That's part of this constructor here. Anyway, what's the next step after that? We sent a vector from one process to another, and then we sent it from one process to a whole bunch of processes. So let's consider adding in the functionality of sieving a specific multiple of a prime number. Let's start with the number 2, because that's the first prime number, and in terms of prime numbers, it's the odd one out. Or should I say it's the even one out, because it's the only even prime number. Anyway, rank 0's job is going to be filling the array with numbers. I really should say vector, but it's going to fill a vector with numbers and then send it to other processes. If we want the sieve to work, we can denote marking non-prime numbers by replacing them with 0. So, 1 is not considered prime for mathematical reasons. So, number 0 is going to correspond with the number 1. So we replace that with a 0. Yeah, for our purposes, we're just gonna cross that out immediately. So, now when we send this vector of numbers, it's not gonna have the number 1 in it anymore. Rather, that number is gonna be replaced with a 0. So, the code here is barely changed. We're just filling it with zeros and say, hey, I don't want the first one anymore. Replace that. So technically another way of doing this is for int I equals 1, so that the number, what would be the number 1 would be skipped. So that's a slightly faster way of doing it, or a slightly shorter way of doing it, because this numbers vector was initialized to be a vector full of zeros. We set one of the zeros to 1, and then we're setting it back to 0. So, moving on. For the other processes, to sieve the multiples of 2, we would need to parallelize the for loop. Now, if we just wrote this for loop, it's actually going to work, but it's going to work correctly, incorrectly. And by that, it's going to do a lot of the same work redundantly. If just wrote it as is, then every process will be redundantly doing the same work. Rather, we want each process to do a portion of the work, but collectively they're all doing all the work. Here we start the loop at I equals 1 because that corresponds to because that's the index for the number 2. And here we have I plus equals 2 because we want to skip every other number because we only want the multiples of 2. This value here, if we're incrementing by something that isn't 1, that's a stride. And this happens quite a bit. In graphics, for example, you might have a vector of values, but every 3 values corresponds to an RGB color value. So if you had to process a vector full of values, you would have to read every 3 values and then increment to the next 3 values after that. Also, this code has another problem. If we left it as is, what's going to happen is, since it starts at 1, any process that's going to execute that code is also going to cross out the number 2, which is actually what we don't want. But we can use this. The fact that it starts at 2 is a bit of an advantage. So maybe let's start rewriting this so it does work properly. So if we want to parallelize this for loop properly, what we need to do is we need to specify for each process a different starting index, and then we have to calculate a stride for each for loop. No, for each process. By multiplying the rank with the current prime of 2 and adding to it the index of where the number 2 is, we can get the starting index for each process. For this example, we're going to be using 4 processes. So we have rank 1, 2, and 3 having different starting positions, starting indices. For rank 1, that's starting index is 3. For rank 2, that's starting index is 5. For rank 3, that's starting index is 7. And those correspond to the numbers 4, 6, and 8. But we don't have rank 0 because rank 0's job is literally to send messages to and from other processes. So, because rank 0 is not involved here, we will never cross out the number 2 by mistake. We also need to adjust our stride so that each process is doing separate work. Instead of incrementing by 2, we increment by 2 times the number of processes we have, minus 1, because, again, we don't have rank 0 involved in this part. So what does that look like? I'm going to open up Excel, and I'm gonna open up Excel, and then I'm just going to zoom in. 1, 2, 3. I'm going to create. I'm going to represent a vector of numbers this way. So 1 is crossed out. 2 is our starting index. But we don't want to cross that out. Process 1 is gonna start. No, all 3 processes are actually gonna start at the index corresponding to the number 2 in the array. But they're all gonna go up by 2s. So process 1 had rank 1. So it's going to start at, maybe I'll just write this in. So process 1 is going to start at index 1, but then so is process 2 and 3. But they're going to use their process ID or rank to figure out how far from index 1 we have to start. So for process 1, it's going to be rank 1 times 2 plus the index of 1. So P1 is actually going to start here. Oops. P2 is going to start here, but it's going to add to this index here. It's rank times the current prime number. So it's going to move up 4 positions and start here. P3 is going to start here, but it's going to add to its starting value, its starting index, its rank times the current prime number. So it's going to go up 6. So it's going to start here. So when this code starts, so when these 3 processes run their for loops for crossing out numbers, what's going to happen is this. So I'm going to use different colors. I hope you can see this. So I'm going to try to use different colors, and I'm just going to hope you can see this. Colorblind accessibility concerns come to mind. So what happens is, this. And although our example is for the numbers from 1 to 10, there's no reason why we have to stop to 10. We can scale it up. So P1 is going to go up by 6s because we have, it's going to go up by 6 because it has to skip the work of not only the other processes, but it also has to skip the work of, it's going to also have to skip any number that is not a multiple of 2. So it goes up by 6s. So P2 also goes up by 6s. So P3 also goes up by 6s. So So P1 is going to cross out 4, 10, 16. P2 is going to cross out 6, 12, 18. P3 is going to cross out 8, 14, 20. I like to describe this as the 3 processes leapfrogging over one another, because that's literally what's happening. They have a stride value that says, they have a stride that makes them skip a whole bunch of numbers, but the numbers that they're skipping are either numbers that they don't have to cross out, or numbers that other processes are already crossing out. So, collectively, any one process is going to cross out about a third of all the required values being crossed out, but collectively, they're all going to cross out all the numbers we need to have crossed out. And that's the basis of how we can parallelize a for loop. If you want a more general format for that, it would look a bit like this. If we have int process ID and int, if you have int process ID and int number of processes, if you want a parallelized for loop, we would write in something like this: for int I equals process ID, I is less than, let's call it loop amount, or I'll just type in the number 1000, or 10. I'll just type in the number 1000 because that's just a number. Let's pretend we're doing 1000 iterations divided by however many processes we have, and then I plus equals and that's the basic format if we have a for loop where we have some number of processes doing some amount of work, but we're dividing that work among multiple processes. OpenMP does something a little bit different from this, but if we had to code it ourselves, this is more or less how we have to code it. In the case of the sieve, we had to add a few more considerations. In the case of MPI, we have a few more considerations. One, we have to find out where our starting index is, because we're not starting at 0. We're starting offset from 0. So we have to start at an index that corresponds to our current prime, and that offset is going to be 1. We multiply by the rank in current prime, but again, we don't want to cross out the number 2 itself. But because rank 0 is never involved here, we don't have to do any sort of plus or minus or anything extra like that, because if rank 0 is never involved, there's never going to be a situation where rank times current prime equals 0, so there's never going to be a situation where one process is ever going to cross out the number 2, because rank 0 is never involved. And then we have to adjust our stride. The stride is whatever the current prime is times however many processes we're dealing with. No, however many processes we have to work with. So we're supposed to have 4 processes, but one of them has the job of sending messages to all the other processes. So really, we only have 3 processes for which we can have this parallelized work. So that's what's going on here. That's probably the core of what I have to explain about parallelizing a for loop by hand. If you did not have the luxury of using OpenMP, this is how you would parallelize a for loop. So, with that, one other thing we can do is swap this print. One other thing we can do is move some code around, so we have the print function, no, the print code here running after all of this here. So, it would look like this if we were to run it. So, maybe what I should do is go back to Visual Studio, grab the relevant code for that. That's going to be main3.txt. Copy, paste, and now we have this modified code. So, all the other processes are going to do something related to... All the other processes are basically executing a parallelized for loop. This other process is just sitting there, sending messages to all the other processes. But now rank 0 has the important job of giving all the other processes something to sieve. So what does this look like if we run it? Well, I have command prompt opened up here still, so if I run it again, so check this out. Rank 0 is sending some numbers, rank 1 has received and then sieved some numbers, 2, 3, what's supposed to be 4 is now crossed out. But it didn't touch 6 or 8, but it did cross out the number 10. Rank 1, 2 is not crossed out because they're not supposed to. It didn't touch the number 4, but it did cross out the number 6. Rank 3 didn't touch the number 2 because it's not supposed to. It didn't touch the number 4. It didn't not touch the number 6, but it did cross out the number 8. So, collectively, each process has done a portion of the work, and if you're just to consider any one process, then the work is incomplete. But if you consider all the processes, then 4 was crossed out, 6 was crossed out, 8 was crossed out, 10 was crossed out. If you consider the work across all the processes, then we have completed all the work that we needed to do. So, when it comes to the sieve of Eratosthenes, we now have the next step of somehow transmitting this new information back to rank 0. So now, we have to return to sender. So this is simple to do. For the code for all the other processes, in the else block, we just have to slap in MPI send. It's going to send back because all the other processes use its numbers vector to store the message that rank 0 is giving out to everyone else. It's gonna send it back. It's gonna use it. It's gonna use the data in that vector and use that as a message, and then it's gonna send that back to rank 0. So number 0, numbers dot size MPI int 0 because the receiver is 0. For rank 0, we can take the code that we had for sending all code to all other processes, and then we can just modify it a little. So, here we have another for loop. This for loop is basically this entire outer one here. Don't worry about this inner for loop just yet. Here we're gonna look at the outer for loop. For int I equals 1, I is less than comp size, I is less I plus plus. So, it turns out we need another vector with which to store the values that we're receiving from all the other processes. So here I'm going to declare a temp vector of, I have search max, but really that's because I was getting a bit ahead of myself and getting ready to scale this up. But really what this should say is vector int temp vector 10, 0 in parentheses. So we're going to use a temporary vector to store the values that we're receiving from all other processes. So really that's actually what's going on the previous slide. We use a temporary vector to store what we're receiving from all the other processes, and then we can use another for loop to store the incoming message into the temp vector from all the other processes. But as is, what's happening here is we're not doing anything with the message that we're receiving, and it's just going to be overwritten. It's as though you were expecting like 3 emails, but each email deleted the last. Not good. So what this inner for loop here is this. We use another for loop to iterate through the temporary vector and replace only the values that were modified, only the values that were changed to 0. But it turns out that's inefficient, because we're checking numbers that weren't changed at all. We're going through all this work of parallelizing code, so we may as well take a page from the else block and do this. Since we had come up with code for the other processes that determines where to start and how much to increment, let's just reuse that. But this way we're skipping values that we don't need to consider. Remember this? If rank 0 is going to be receiving values, what rank 0 needs to do is ultimately produce a vector that looks like this, where every other number is 0. What rank 0 is receiving is vectors where not every vector, none of the vectors is going to have every other value be 0. It's going to have like every 6th value be 0. So it has to combine those vectors somehow into 1. So this for loop here, we're going to have to modify it so we have a different start index, and then we have a stride. The only change here is to replace rank with I, because rank, if it's rank 0, rank is going to be 0. So we have to deduce what process, what rank did that work. If process 0 is going to receive the vector from process 1, it's going to have every 6th number be 0. But guess what? We're in a for loop that iterates through all the process IDs, 1 to com size. So let's just use I. So the current prime is 2, the starting index is 1 times I times current prime. The stride is going to be current prime times com size minus 1. And then we have this for loop here. For int j equals starting index, j is less than temp vector dot size, j plus equals stride. So now, what happens is we're going to cross out numbers. We're going to cross out numbers. Or rather, rank 0 is basically combining all the vectors sent from all the other processes and combining them into an updated vector that looks like this. So ultimately we're gonna get an updated vector where every other number is crossed out and replaced with 0. So that's what's going on here. I do have an alternate implementation which I'll get to shortly. And then we can just print out the whole thing and let's do a checkpoint. I have the code written up all here already, so I'm just gonna copy, paste, and rerun this whole thing. MPI exec-n with 4 processes, and it's gonna run a little bit because I accidentally set to 1,000,000, but here we are. Right, 0 is sending some numbers, and I forgot to build it. Build. Control-Shift-B to build. And then clear. Try again. There we are. Rank 0 is sending some numbers. Rank 1 received and sieved some numbers, so rank 1 crossed out the numbers 4 and 10. Rank 3 received and sieved some numbers, but it only crossed out the number 8. Rank 2 received and sieved some numbers, but it only crossed out the number 6. What rank 0 has to do is combine all of these vectors into one single vector where every other number is 0. Except for 2 and except for 1. Those are the only ones that break the pattern. But now we have an updated vector with sieved out numbers. Now for that alternate implementation. This alternate implementation is a lot simpler in that rank 0 doesn't have to worry about a stride or anything like that. Here's how it works. Remember how I said we can declare our own variables within these code blocks? Yeah, remember how I said a while ago where if we declared a variable here, this other code block won't know it exists, and vice versa? Well, I'm going to write in a vector. It's going to be of size 0, and it's going to store the indices of non-primes into its own vector. Yeah. So for all the other processes, they're going to be storing, they're going to store the indices of non-primes into a vector. We're going to use the same starting index stride combination as before with the for loop, and instead of what we're going to do on top of this is numbers I equals 0, but it's not going to send that back anymore. Instead, it's going to push back the index I that corresponds to a non-prime number. And then it's going to send back this entire vector that's full of the indices of non-prime numbers. So for this to work, we need to do 2 sends. The first thing we send is the number of indices. The second thing to send is the indices of all the non-primes. Can you do this? Is it possible for us to do this without having to do a pushback? Because pushback is not a big O of 1 operation. We say its amortized time is big O of 1 though. And that means like on average it's more like, yeah, on average pushback is gonna be big O of 1, in reality it takes time to do a pushback operation, because if you have a vector that's filled with numbers and you try to do a pushback and there's no room, the vector has to allocate a new array twice the size as before, copy all the old values into the new array, and then push back. I think it would be possible to do that, but for that to work, the worst space we would have to do is like, I think the worst amount of space that we would need is to have a vector of indices of non-primes be the same size as numbers. But slightly more efficient than that would be to say 1/3 that size, because we only have to deal with 3 processes. But anyway, this is one way you can do this. There are possibly other ways to do this more efficiently. So when we send this, we're going to send the number of indices and then the actual array of indices of non-primes. For rank 0, we have a for loop that receives the arrays from all other processes. But instead of arrays of crosshat values like this, it's going to be the indices themselves. So really, if I'm going to be using this as an example, we're not going to receive this. We're going to receive these values. These are the indices of non-primes. So, first thing we need to do is we need a variable in which to store the number of indices. So int number of indices, int mpi receive address of number of indices 1, mpi int I 0, mpi comworld, mpi status ignore. So we need one receive function to receive the number of indices, and then we need to use that information to create a vector that is of the correct size to receive the vector of indices. So here, vector int temp vector, and it's of size number of indices. That was the first value we received. The second thing we received is going to be stored in this temp vector. So address of temp vector 0, number of indices, mpi int I 0, mpi comworld, mpi status ignore. Since we have the indices of what was found to be non-prime, we can just iterate through this array of indices one by one, as we normally would with most other for loops. So for int j equals 0, j is less than number of indices, j plus plus. We get the index from the temp vector, which is the vector that contains our indices of all the non-prime numbers. And then in the numbers vector, numbers index equals 0, we use that index. We use these indices here to replace all these numbers with 0. So the hope is this. If we parallelize the work of finding out what the indices of non-primes are, hopefully we can reduce the time it takes by parallelizing the process of finding the indices of these non-primes, we can hopefully reduce the time it takes to do that. But then it's up to rank 0 to go through all of that, and then it's up to rank 0 to figure out what to do, how to update the values needed for that. So if we tried this code instead, I have it all written up here. So if I copy paste that, here we have if rank equals 0, we have the code for receiving the arrays from all other indices, but this array is going to be the indices of non-primes. Here in the else block, we have the process is storing indices of non-primes and then sending it along with the number of indices to send back to rank 0. If I build this and run that, if I clear this and I run it, it's going to work the same as before. Does this make a difference? I am not sure. Because really the main point is trying to parallelize it, not so much try to... The main point is trying to parallelize it. The main point is trying to parallelize this algorithm. Not so much reduce the execution time down to the very last microsecond. Which I guess parallelization does that to an extent. It's just that optimizations that are related to execution time aren't exclusive to parallelization. So, in summary, implementing the sieve in MPI requires some thinking, but it is possible. We have one process that's going to send to all the other processes and then receive from all other processes. All other processes will then deduce where the indices of non-prime numbers are. Or it's just going to cross them out entirely. It's going to send those vectors back. Rank 0 is going to have to process that information to create an updated array of values. So at the end, we would have something like this, where, at least at the start, we have every other number crossed out. But that's just for crossing out the multiples of the number 2. The next step is to do the same process for multiples of the number 3. And then the next number after that. And then after that. This is going to be code for the next video. So in that video, we're going to scale it up like big time. What this is a starting point for sieving out just the prime numbers. No, just the multiples of 2. The next thing we have to do is iterate to that next number. But again, that's going to be for the next video. Alright, so hopefully this video is really helpful for you. It's a bit on the long side because it's so technical. We're nearing the end of the semester, and that's why I want to make this, and that's why I really want to make this video. It's going to be 2 parts because there's just a lot to go through. The next video is going to be part 2 of this. The next video after that, I would like to be a sort of intro to NVIDIA CUDA, because NVIDIA CUDA is a lot really interesting. So I'm not going to ask you to program anything in NVIDIA CUDA because you might not have the correct resources, and I'm not sure if the lab has those resources for us already. So at the absolute worst, I would at least want to show you what it looks like. And since your final project, we had a midterm project, and that was the OpenMP benchmarks. Your final project is going to be MPI benchmarks. So this is why I want to get this out as soon as possible. So that way you have ample time to write a sieve in MPI and then benchmark it. Okay. I know this is an async I know this is a hybrid class, so if you are capable of doing this on your own, then more power to you. But if you need help, you are always welcome to come into the lab, into the Monday class sessions for any assistance. Regarding the sieve of Eratosthenes, I know you have your MPI times table. That should be due sometime this week. I'm going to be I'm gonna start grading your assignments. I'm gonna start grading whatever assignments you have, and hopefully in the coming weeks we'll be making progress on what to do with for the NPI sieve, because as I said, your benchmarks, when you do benchmarks for this, that's literally your final project. So yeah, it takes a bit of time, but if we take it step by step, it's gonna be possible for us to actually write this entire program. And this is just the part 1. So part 2, if possible, I want to record part 2 as soon as possible. So as soon as I'm able to. I have some other plans today, so yeah. Might not happen today, but for those of you who are in my other class, this is why I had to cancel. For those of you who are in one of my other classes, this is why I had to cancel it. I have other plans for today, so yeah. That's why I'm in a bit of a rush to record this right now. So anyway, for CSE-5250, follow this PowerPoint, follow this video, try it out for yourself, see if it works. Come back on Monday if you have any issues, and then we'll continue off with part 2 of this entire thing. Alright, see you next week.